Chapter 7, understanding the processor. So just to recap on the stuff we've covered in previous chapters, especially for those of you who haven't been, atomic operations are indivisible. This is kind of crucial to why we use atomics. Atomic operations in Rust are done through atomic types such as atomic I32. And the reason we use them is so that all the changes to a single atomic variable appear to occur in a single total modification order specific to that variable, which means that you can't get, for example, an atomic I32, if you increment it on one thread and you increment it on another thread, that's never going to happen such that you only get one increment. So that, for example, they both read the old value as 3, and then they both tried to increment it to 4 and store 4. So then instead of adding 2, one from each thread, you've only added 1. That's never going to happen with atomics. When you're dealing with multiple variables, so there's other memory at play that could be shared, then the relative ordering of atomic operations becomes really important. And that's what a lot of this was about, and also a lot of what chapter 3 was about earlier in the book. So what is actually happening when we use an atomic type and these atomic operations? Well, generally, you can think of it as there are certain instructions that give you this atomic behavior, and there are other sets of instructions that don't. We are going to talk about the processor instructions that are available to us, caching and how that affects the whole story when you're dealing with atomics, and memory ordering. So when we compile code, we obviously generate machine instructions, and those are going to be specific to the processor we're targeting. So most people tend to work with x86 or ARM64. So those are the two ones that are going to be discussed here. That's the ones that Mara uses in the book, and I'm sticking to the book very closely. Different processors have different machine instructions available, and that affects how our Rust is going to look when it gets converted into machine instructions, and what the implications are then of how you do things in your Rust code, what ordering you use, etc., will depend on the architecture. And we can view the generated assembly, which is like human readable machine instructions, using Compiler Explorer, which we're going to be doing a lot of. If you haven't used Compiler Explorer before, which you might not have done if you're not, if you haven't used C++ much before, or you just haven't heard of it, it's brilliant for viewing how things get converted to assembly. You can view the compiler output you can target different architectures, you can add different compiler flags. It's excellent. So we'll start with just a simple processor instruction example. Here we are taking a number by reference, and then we're adding 10 to it. And that becomes the following on ARM64. So let's have a look. Pull it up. So here we are loading into the W8 register the contents of this memory address. We're then adding 10 to it and storing it back into the original register. And then we're storing the value of that register into the original memory address. So it's being put back into this reference. And this is what Compiler Explorer looks like if you haven't used it before. And this is with the target being ARM64 or Arch64 with unknown Linux muscle. And if you hover over it, you can see the different parts getting highlighted, which can be useful. Like that's just a return statement. This one's quite simple, but if you're dealing with complex bits of code, Compiler Explorer is really nice for this. Right, let's get back to the slides. Oops. Different tab. Sorry, 1 second. I've lost my slides. Oh, I closed my slides. There we go. Right. Whereas on x86 or x64, so if I change that target to be x86, then I'm going to get a totally different looking assembly. So here it's the same kind of operation. So if you go back to the previous one, we still have an add, but this time, instead of having to do a load and then an add and then a store, on x86, we just have a single add instruction that is able to do that load from the memory address and the adding 10 to it, all using one instruction. And that doesn't mean that it's faster necessarily. It's just different. So we introduce this idea of a reduced instruction set versus a more complete one. So here is another example. So this is comparing side by side, the exact same one. As mentioned, into register W8, we load the value at address X0, add 10, store it, store the value in W8 into the memory address at X0, whereas on a complex instruction set, that's just one step. With atomic operations, so you can see immediately how this is going to be a problem. You can't really tell if this is a problem, but you can see immediately this could be a problem because these are all separate instructions. And if you were there for previous chapters, you'll know the main point of atomics is that you're doing it as a single step, so nothing can get in between. Because the problem here would be, okay, I load it, and then I maybe try and increment it by one, but a different thread might have also loaded that data. They'll have their own little local version in W8, and then if they increment it and try and store it back, well, we're both going to be trying to store back potentially, incorrect values because we don't know about the other modification that's happening simultaneously. So the atomic operations you can think of are going to be store, load, read, modify, write, and compare and exchange. Now, within Rust, there are like different atomic operations available on different types that you can see, but they all kind of boil down to these four. So if we take the store example, so in this case, we're again taking I32 by reference, but this time we're just going to store a 0 into it. And we can compare that to the atomic version, which is going to be taking an atomic I32 by reference. Now, obviously, atomics have interior mutability, which is why this isn't mutable. But it's the same premise of we're then storing a 0 into that atomic I32, and we can compare the different assembly that gets generated. So for an atomic I32 store, we get identical assembly for whether it's atomic or not atomic, which might be kind of surprising. So on ARM64, this is what it looks like. We're just storing the 0 into X0 address. And on x86, it's very similar. We're moving a 0 into this RDI memory address. And with load, we also get identical assembly for I32 versus atomic I32. So you might be thinking, well, why do I even need atomics? It's already atomic, kind of. And for basic operations like this, it is. It's essentially, it happens to be on these architectures, but there's no guarantee that it will be. But when we look at the assembly, that's what we see. We see that in the case of a load, we are loading the value of X0 into W0. And on x86, we are loading the address IDI, the data at that address, into EAX. Where read-write is where things start to get a little bit more interesting. So in this case, we are taking this mutable reference to an I32, adding 10 to it, and storing that back into the I32 again. On x86, this ends up looking like a single add operation. So nothing particularly interesting there. And here, again, this is the one we saw earlier. So we're loading it in. There's nothing special, but we can see that there's going to be a problem with this being atomic because there's multiple instructions going on here. On x86, as I mentioned, even though this looked like one instruction on the previous example, just using a regular I32, we can see that it wasn't atomic by the fact that when we compile it as an atomic, we get this additional lock keyword. And what that does is it ensures that the processor has exclusive use of any shared memory. So that means you're not going to get two threads trying to write to it at once. You're not going to get this, we're both incrementing it and then we're trying to store it back. None of that's going to happen. And similarly for ARM64, so we don't have this single instruction. We don't have this notion of just adding a lock prefix, but we do have the idea of exclusive access. So there's this load linked exclusive, this load exclusive, which is an example of like load linked here. So what this does is it ensures that when you come to store the value that you thought you were getting exclusive access to, it checks that you actually did have exclusive access. So same type of deal where you're loading the data at X0 address into W8, then adding 10 and storing it back into W8. And then we've got this store exclusive again, like here, which is different to a regular store because it's conditional. So what it does is it tries to store the contents of W8 into this address X0. But if this address X0 was accessed in any way between this load and this store, so there's separate monitoring going on to make sure that X0 wasn't read from, wasn't modified, sorry, then, or even read from potentially, then it will store a 0 in W9 if it succeeds. So if it manages to do the store, then it stores a 0, and then it says, okay, if W9 is non-zero, which means I didn't manage to succeed in the store, then I'm going to go back and I'm going to try again. But if it is 0, so I've managed to do the store correctly, then it's going to return. So it's essentially like a little loop where it tries to get exclusive access and store it. But because there's multiple instructions going on there, it has to do this little loop because it doesn't know that it's definitely kept exclusive access during the add, between the add and the store operation. So we kind of just discussed this. So the store can fail, basically, and then it can retry. If W9 is non-zero in this case, then it jumps back to the start to retry. This might kind of remind you of a compare exchange loop, and it is kind of quite similar. So compare exchange operation checks if the atomic value is equal to a given value, and only if that's the case does it replace it with a new value. So it's similar but subtly different to what the what this load length store conditional was doing. There is also compare exchange weak in Rust, which has the same condition of you can only store the value that you want to store if the old value is what you expect it to be. But what makes it different to regular compare exchange is it's allowed to fail. So the value can be unchanged, but it can still fail to store it. And you see that you can see how that's going to interplay with this when we look at an example. So on ARM64, this compare exchange weak uses that same kind of load length store conditional pattern as the one we saw with fetch add. So here we are loading it and we want that to be exclusive. We check if the value is what we expect it to be. And if it's not, then, well, we know that's going to fail. So we go to L1, which clears that exclusive access request that was created with this LDXR, the load exclusive instruction, and then returns. But even if it did succeed, so even if the value was unchanged, we saw the new value into W8, but then this store exclusive can still fail. So we've still got this additional conditional check. So even though the value hadn't changed, so the compare was fine, but potentially this memory was read for some reason, or something else happened that means that it thinks this store is not allowed. So as a result, it's going to just return because weak is allowed to spuriously fail. So even though the value was unchanged, we succeeded on this compare check, we can still fail here. And then if you had the compare exchange, so you want it to never spuriously fail, then you just end up with an additional retry loop. So here, if this actually failed to store, so W9 was non-zero, then you would go back and you would try again. If the value was different, it would still just be like compare exchange weak, where it would still fail as normal. It's not doing a loop when the compare fails, it's doing the loop when the store fails because something else accessed that memory. Just going to have a quick look at the chat, see if there are any comments. Oh yeah, someone mentioned about cargo show ASM. So yes, Compile Explorer is like a very quick and easy way to view the assembly, but there are multiple other ways you can get the assembly out of your program. And I think Cargo Show ASM is a tool that someone's written that takes away a lot of the kind of noisy assembly and it does something very similar to what Compiler Explorer does, but it can be really useful if you're doing this for like a real program that you really want to see what's actually happening. Okay, so we talked about compare and exchange on ARM64, but on x86, there is actually a compare exchange instruction that you can just use directly. So again, because we're in this kind of atomics world, and this might look like it's a single instruction, but there's subtleties at play. So you still need this lock keyword. So this lock instruction or lock prefix blocks the other cores from accessing some or potentially even all of the memory. You don't know how heavyweight this lock is, but it it's going to make sure that you have exclusive access to the memory. So it's very similar situation here. It's taking, so in EAX we have, so if we go back to the example, we were comparing and exchanging 5 and 6. So we're checking if the value is 5, it's going to implicitly check the EAX register. Compare and exchange, so we're saying if this value is what we expect it to be, which is 5, then put the contents of ECX, which is 6, into it instead. All right, which brings us on to the next section, which is processor caching. So reading from and writing to main memory in the context of Rust and C++ world is generally considered slow. And modern processors typically, instead of reading and writing directly to memory, will have one or more caches, will be in between the memory and your process. So a naive processor might check if a piece of memory is in the cache. If it is, retrieve it. If not, then get it from the main memory, which will be slow, and then cache it. Once the cache gets full, drop some of the older cache entries. And similarly, your writes might only live in the cache for a short while until the collective changes need to be written to main memory. So you might think you're writing to memory, but maybe you're only writing to the cache. And then after some amount of time, that might write to memory. But when you start introducing those caches, you can see there's a whole host of problems that can start to appear. When you're reading from main memory, because it's slow, rather than just reading the specific bytes that you need, you tend to read a cache line. So the cache line might be a block of 64 bytes. And that will mean that instead of just reading your 1 byte of memory and then, oh, I need the next byte of memory, I'll get that one now. And you're doing multiple requests all the way down into the memory, which can be slow. You request the entire block of 64 bytes. And then if you need the next block of memory, well, you've already got it in the cache, even though you hadn't requested it yet. And this can be one of the reasons why compare exchange weak might spuriously fail, because even though the value hasn't changed, no one's actually accessed that memory. If someone's accessed the neighboring memory, well, then that cache line has been invalidated. Someone else has said, okay, I've already used that cache line. You don't know, the processor can't figure out whether or not it's used your bit of memory or just another bit of memory that was in that cache line. So it will fail that store, and you'll end up failing your compare exchange weak check. As mentioned, there can be multiple levels to your cache. So L1 would be the first cache, the fastest one that gets accessed, then L2, possibly L3, could even be an L4 cache. And when memory is written to, the caches need to make sure that there's some kind of consistency between those caches that different processors have access to. There needs to be some kind of consistency. And there's a number of different what's called cache coherence protocols that are used to achieve that consistency across multiple threads. Because you can imagine, if thread 1 is only writing to its own cache and not actually writing to memory, and thread 2 is also only writing to its cache, well, those are totally separate. And then when they both come to eventually store in the main memory, well, they're gonna be incompatible. You're not going to get that atomic behavior that you were looking for. One protocol that you could adopt is the write-through protocol, which is one of the simplest. It means that writes, so if you are actually modifying memory, will be immediately sent through to the next layer of the cache and go all the way down to memory. So they won't actually cache any writes on the way. And other caches then can observe the other cache's communications to the next layer through some shared communication channels. So you can see if another cache has written some memory. And if the cache observes a write for address that it has cached, then it's just going to immediately drop that cache or update its cache line to keep everything consistent. So it's looking out for writes. If it sees a write, then it's going to invalidate its own memory and either drop it or update it with the latest value. And that means that we don't actually get any caching benefits for write operations because we're going all the way down through the caches every time we write. But if we're reading a lot, well, then that's not a problem, because all of those reads can still be at those cache lines. That they can read from L1, it can read from L2, and as long as there's no writes going on that are invalidating it all the time, then you will get that performance benefit. But for writes, it's going to be pretty inefficient. So this is the general process. I found this on Wikipedia. You have your memory request. You go in, and if it's a read, then it's just a straightforward, okay, do I have it in the cache? Yes. If so, return the data. Done. If it's not in the cache, find the cache block to use, read the data from low down the memory, return the data, and then done. For writing, you don't have any of that kind of circumventing the memory. You always go down into memory. If it's not a cache hit, then you just go all the way down and write it into your lower memory. But if it is a cache hit, then you're going to write the data into your cache block, and then you're going to store that value all the way down into the memory. There's also something called the messy protocol, which is built around the idea of setting a state for a cache line. And there are 4 possible states that it uses to figure out what it needs to do next. So a cache line can either be modified. So if I'm doing a write, then that write is going to be modified. You've got a modified cache line that's going to contain that data that's been modified, but not yet written to memory or the next level of the cache down. Exclusive cache lines contain unmodified data that's not cached in any other cache at the same level. So you have exclusive access to it. Shared cache lines are unmodified, and they might be in one or more of the other same level caches. So you don't know, you don't have exclusive access to it. And invalid is just for unused, empty, or dropped cache lines. So you can't use the invalid cache line. You would have to go and get it from the lower level of the cache, or another one of the caches at your level. So if there is a cache miss, then other caches at the same level are checked before going to the cache level down. So you could think of the messy protocol as being like a very tier-based system, where you check your own tier before you check the next level down. If a cache at its level does have the cache line that you're interested in, then it checks, okay, well, is their cache line shared? It is shared, great. Then I can just have a copy of it, and I will also have a shared version in my cache. If the cache that it's getting it from has exclusive access to that cache line, well, I'm getting a copy of that cache line, which means it's not exclusive anymore. It needs to get marked as shared. If I try and read it from another one of the caches and it's marked as modified, well, I can't read it immediately, because then we would both have the modified version, and then we couldn't have it as shared access because it's modified. So instead, the value gets flushed, which means it gets written down to the next layer, and then the cache that I am reading it from gets marked as shared, and I get a shared cache line as well. If none of the caches at the current cache level have the memory that I want, then it's going to retrieve it from the level below, cache it, and mark it exclusive, because you know that no one else at your level has that cache line, because if they did, you would have gotten a cache hit at your level. So not in your cache, but you would have had another one at your level. Let's check the chat again. Writing can be slower if you have a cache hit, because you write to the cache and memory. I think it's still faster than a cache miss, because the cache, generally going down the tiers is where it gets slower. That's the method, but there is a cost. There is definitely still an associated cost. But I don't quote me though. This is very much not my area of expertise, but I do find it very interesting. If you want to write to something that you have in your cache, then you need to have exclusive access to it, which makes sense for the reasons we just discussed. If you're modifying it, you need to be the only one with it. So if you already have exclusive access, that's fine. You can just write to your cache. But if you don't have exclusive access, then you need to get all the other caches in your level to mark themselves as invalid rather than shared. So that way, they know that you're going to do your write, you're going to do your modify, and then they're going to check you and say, when they come to read that memory again, they say, oh, do you have the cache line I need? You're going to say, oh, yes, I do, but it's modified. And we're going to be back in this state where we're flushing the value down, and then we both have the shared value after the modification. So it's quite a nice system. It takes a little bit of remembering which ones do what, but it does, it's actually not that complicated, I think, probably compared to what I imagine a lot of other protocols for caching are. So this it's manageable, makes sense, but you can see how it gets complicated quite quickly. Generally, you could think is that reading and writing to the same atomic from multiple threads is not as cheap as you think it is. I mean, it is cheap, but it's not free. And that's partly due to this cache coherence. It's having to do this, okay, I've got a copy of it. Does the other caches have a copy of it? Oh, yeah, they do. What do I do then? And writing to an atomic on one thread can slow down the reads on another thread because you need exclusive memory access, which like intuitively kind of makes sense. But I think we do have this impression that with an atomic, everything is just magically instant, and it's not. There are things going on in the processor which allow you to get this behavior, and one of those things is cache coherence. Like, it's fast, it's all, these are very, very small times here, but there is work going on to make sure that you get this cache coherency. It's essentially like a tiny little lock, but it's not really a lock. And having a look at this Compile Explorer link. So Mara's got an example in the book of showing how a store on one thread might impact a read on another thread. So here I've got this atomic that I'm storing a 0 into, and I'm just going to keep storing a 0 in. It's not actually changing the value. Nothing really special is happening there. But then if I then on another thread, I'm reading it, what you'll see is that the time is going to be slower if this operation is a store versus if it's just a load, because a load operation can be done with a shared cache line, whereas a write operation would need exclusive access. So that means you end up dropping cache lines much sooner, because every time this thread needs to write to A, this thread, when it tries to load it, is going to have an invalid cache line because it's going to have been invalidated by this store operation, and then it's going to have to go to that cache and pull the value out. So just having a look at the chat. So caches on the same level means there may be as many level 1 caches as cores, but for level 3 there is just one big shared cache. So I don't think you're necessarily going to have one big shared cache by the cores. So you can still have like multiple level 2 caches. You can have the same number of level 2 caches as cores if you want. So I don't think you necessarily will, but you could have the same, I think you could, someone jump in if you think I'm wrong, the same number of level 2 caches as level 1 caches. It just means that before you go to the level 2 cache, before you check like your own level 2 cache, then you might check the other level 1 caches on the other processors first. You could have a different number. I can't think why that wouldn't work. I don't remember it coming up. So if anyone's got any more information, please drop it in the chat. Someone says you can have several processors. In that case, L3 is going to be separate. Oh, and then there's NUMA and other hovers. So yeah, please feel free to unmute and tell us about it. Definitely consider this open forum, or you can save it till the end. So this was that example that we were just looking at in Compiler Explorer. So on a separate thread, we're storing zeros repeatedly, and the store is requiring exclusive access to the cache line. And even though we're just timing the atomic load operations, we can see if we actually look at the time coming out that it is going to be slower here, even though we're doing the same number of loads on the atomic. And this black box is just to make sure that the compiler doesn't optimize the whole thing. So loading on another thread doesn't cause the same performance hit, and that's because load can be done with that shared cache access that we talked about, which allows your cache, the thread that you're on's cache, nearby cache, to keep its shared cache line, doesn't get invalidated. And similarly, and quite coolly, because these cache lines are taking a whole cache line, not just the data that we need, that slowdown can happen even due to the use of independent but memory adjacent data if it happens to be in the same cache line. So what that ends up looking like is something like this. So here I have an array with 3 atomics in it. These 2 atomics are obviously totally independent of this middle atomic, but we're going to do store operations on these 2 atomics. So the first and the third ones in this array. On our main thread, we're going to be loading the middle atomic, and we're going to see that same slowdown. So if these are loads, then we won't see a significant slowdown, but if these are stores, then we do see a significant slowdown. Now, obviously, this is Compiler Explorer, so I don't have control over the hardware being used, but I did still observe the slowdown. I should have just run it locally instead. But if so that estimated is 32 seconds. Let's change these to loads. That's not that much faster, but I definitely did observe a speed up when I did it. So that's 15 seconds. Just changing spaces to get it to rerun it. 47 seconds, it's super variable. Run it on hardware that you have control of is the lesson there. So this is that example with this atomic and this atomic being written to and this atomic being read from, and we still see a slowdown there. You can get around that by spacing out the data. Not sure there are probably that many use cases where you would actually do this in practice, but I could be wrong. Maybe you have one. But it's cool to see that you can align it so it's 64 byte aligned, which means that each of these atomics are going to be aligned to those cache lines, and as a result, these stores are going to be totally independent of this load, and you're not going to see that slowdown. For single pieces of data, the tools that we've seen so far with relaxed ordering are enough. So where things get complicated is where you start bringing in other pieces of related data. And that's where you have to start thinking about ordering. So just to recap, again, especially for those who haven't been to previous ones, there's these 2 most important orderings to kind of think about are release and acquire ordering. Release is something that you would do on a store operation, and that means that no reads or write in the current thread can be reordered to after this store. So anything that happened before it is going to stay before it. And all writes in the current thread are visible in other threads that acquire the same atomic variable. That means that you're going to be definitely reading the data that you think if you do an acquire on the thing that this is doing a release on. And an acquire is going to be used with a load operation, generally in conjunction with a release somewhere else where it's doing the store. And that means that no reads or writes in the current thread can be reordered to before this load. So all the writes in the current thread release the same atomic variable that release the same atomic variable are going to be visible in the current thread. So this is where you're releasing it, you're writing some memory and you're doing release. And then here you're doing an acquire. From chapter 3, you might remember this example of where you can use this ordering to do safety. Obviously, this is not something you would necessarily do in real life, but here we've got a global here of static mutable data, it's U64, and then we've got this atomic ball that we're going to use to guard our data. Essentially, what we want to do is we want this to always be 123. So we want to make sure that this data write happens before we do the print statement. And there's no guarantee of that if you didn't have this atomic here, because this thread could spawn this, but this won't necessarily happen before we get to the print statement. Here we do a store on this ready bool after we've set this to 123. And because it's got release, that makes sure that this won't get reordered to after. And we then check that with an acquire, which means that everything is going to be visible. So this data is going to be visible because we've done an acquire on this ready. Then we if this fails the check, so we haven't actually set this to true yet, then it's going to keep looping. But once it is true, then we can get through to here and print the data. So there's a pairing of acquire release from chapter 3. And that's important for a couple of reasons. So the compiler, we know, can reorder operations if these ordering constraints are not in place. So if there's no intrinsic dependency, so here, there is no reason that the compiler shouldn't reorder this to be before we store true if this wasn't atomic, because this data is unrelated. There's nothing, connecting them. They're not dependent on each other. So why can't I switch around the order? But by adding this memory ordering of release, you are saying, actually, this order does matter. And it's not just the compiler that can do this kind of reordering. The processor can do it as well. Oh, we're actually got that one time than I thought. The processor has things like it can use store buffers. So a write operation can be slow. So maybe instead of writing a cache line immediately, it might write it in a quick store buffer, and then the store buffer in the background will be writing it and doing all of the cache coherence stuff, but the processor itself is just continuing on with the remainder of its tasks. There are also invalidation queries, so instructions can be sent to say drop that cache line, and those might not happen immediately. It might not drop the cache line straight away. And where one cache might drop it immediately and another cache doesn't, that can cause you to have slightly inconsistent cache states. You also get pipelining, which means consecutive instructions within the same processor can actually be executed in parallel. And if it's executed in parallel, well, then the order's not guaranteed. And different processor architectures have different instructions that restrict or prevent the types of reordering that the processor might be doing, which is why memory ordering is important, not just at the compiler level, but at the processor level. So we talked about acquire and release, or for operations that do both a load and a store, you might have acquire release, where your acquire goes with the load and release goes with the store. No special instructions are needed for x86 for these ordering constraints, and that's because x86 is what it's called in the book and in other places. It's this idea of being strongly ordered by default, which means that you already get this ordering behavior anyway. And that means that your relaxed operations actually already behave like their acquire release. So you don't actually need to make any changes. And you might be paying the associated cost for that, but the cost might be very, very small. Things get a little bit different when you start using sequentially consistent. So that requires a kind of globally consistent order, which is kind of a slightly funny concept, and I'm not 100% convinced I have my head around it fully. But it's the idea that multiple processors should be seeing memory in some consistent order. So if variable A and variable B are going to change relative to each other in some order, so A gets set to 7, B gets set to 3, both processors are going to see A gets set to 7, B gets set to 3 in that order. That is the order that's going to happen. Doesn't mean they happen at the same time. It still might happen later or earlier, depending on when it gets read and where it's from the cache and what's going on with your thread. But it is going to have some globally consistent order. So the way it does that is it has these additional instructions. So this is just setting EAX to 0. This one here is doing this exchange operation instead of a basic move. So the reason it's doing an exchange, even though it doesn't care about the value that it's reading out, it's just writing, it's just storing a 0. But instead of using a move to just store the 0 in, it's going to do a read and a write using exchange in order to get this additional ordering constraint. So that way, because it's both a read and a write, and x86 has that kind of strongly ordered behavior, just by switching it to this swap operation, you are going to prevent that reordering and you're going to end up with something sequentially consistent. On ARM64, you do need some special instructions because ARM64 is not strongly ordered. It does have this reordering behavior, which can give it room for optimizations, but also means that you can have, if you haven't got your ordering correct in your code, you can end up writing incorrect code that has really subtle bugs related to the memory ordering. So your store operation, instead of doing just a regular store, you're going to be doing a store release register, which means you're going to get the release ordering. With load, you're going to be using a load acquire register. And then for loading exclusive access, so that was when we were doing like the fetch add, then you're doing load acquire exclusive register and store release exclusive register. And that's the one that can fail the store exclusive if it doesn't have exclusive access. So that fetch add again, so this is the same loop for access, but now instead of having relaxed ordering here, we've got acquire release, and you can see this operation has changed so it was store exclusive, and now it's store exclusive release to prevent that reordering. I'll be showing the Compile Explorer actually. Things can go wrong if you get it wrong. So this is the example from the book. So you can acquire the lock with the wrong memory ordering, and then you can release the lock with the wrong memory ordering. And if you do that, this counter, so this is spawning 4 threads, each of which is doing 1 million iterations to add to the counter, and you would expect that to give you a consistent result, but it doesn't necessarily, depending on what architecture you are. So in the example, she's using like an M1, I think, Mac, and yeah, 2021 Apple iMac M1 processor, ARM64, and it was out by 0.4% after this many iterations, which again, not a huge amount, and just enough to drive you crazy if this is a real bug in your company. So yeah, it's very important to get right. It's kind of subtle, and as you can see, there's a lot of places it can go wrong, not just at the compiler level, but also inside the processor itself. And that's why these additional atomic instructions exist that allow you to put that ordering into the actual processor instructions to prevent the reordering. So, whistle stop tour. Different architectures have different instruction sets, and x86 64 has specific instruction operations such as fetch and modify that look like they're a single operation, but you still need to lock them if you want to have that indivisible behavior that you need with atomics. ARM64 uses a load linked store conditional pattern for fetch and modify, which sometimes might need to retry if that cache line gets read from between loading and storing. Caches operate on cache lines, which means even though the data you're looking at might not have actually been modified, you still might end up invalidating the data you're looking at. And ordering is really important to control at both the compiler and processor level. And that was chapter 7. So do you want to open up for like conversation? What do people who managed to read the chapter think of it? And yeah, any questions as well, I guess. And I'll do my best to answer, but there might be someone else in the chat as well who might be able to answer better than me. Oh, someone got an emergency alert. How did everyone find that? Oh, I can.
What struck me the most, I guess, was what I mentioned at the beginning, was that this is just 2 processors, and Rust compiles to a whole bunch of other processors, and this is just so complicated.
Yeah.
You know, if we're trying to write our programs, figuring out, you know, if we have any hope of having our programs sort of compile to all of the things we're interested in, it just, I don't know. It just makes my mind hurt.
It's amazing that any of it works. Oh, can't hear you there, Michael. There's something strange going on with your audio. You sound like you might be an alien. I can tell that you're not, but one of the things Mara says in the book as well is that some of this, like the knowledge of like how these things are working under the hood, is proprietary, which means you can't even like reason about it with any degree of certainty, because it's only when a bug appears that you actually end up finding out a little tidbit of information about how it's actually happening under the hood.
Is that any better?
Yes, yeah, that's much better.
Yes, so support for all the different processors coming from LLVM, not from Rust compiler itself.
Oh, okay. Yeah, that makes sense. Thank you, LLVM, for all your work.
Excellent summary, Ciara. Thank you for all that. I was just wondering if anyone had any real life experience of trying to apply these mechanisms using atomics to try and get better coherence while keeping performance.
Yeah, that's how you write multi-threaded programs. Like if you used Arc, or if you used, what's the other one? You would be using atomic instructions internally. So if you want to share mutex across multiple threads, you will put it inside Arc and share that.
I guess, Richard, was your question more about how hard are you thinking? How many people here are thinking really hard about memory ordering when they're doing it, like as in having like, you know, a lot of this gets wrapped away for us, like in, you know, like say in things like Arc, where the, you know, the atomic's hidden and mutexes handle so much for us. But if you're dealing just with the raw atomics yourself and using that manually to manage the coherence between, you know, your data and making sure the ordering is correct, because C++ defaults to sequentially consistent, I think, which gets you in the mindset of like, oh, well, I'll just use sequentially consistent everywhere. But now we're seeing, oh, okay, but that's causing these additional instructions and potentially like removing optimizations. Like, how have any people like eked out extra performance in their C++ by not using sequentially consistent?
Well, at some point I had to share data between two different threads. The channels were introducing a bunch of extra latency, mostly because when it blocks on trying to read from the empty channel, it's tens of microseconds. I think that's a lot in my case. So I ended up using atomics and to operate with bigger chunks. It kind of helped a bit.
Yeah, for me, it was really helpful, especially this memory ordering things and the compare exchange operation, because in my PhD, I wrote like kind of a thread pool with worker threads, and they had like this state. There was an atomic, but you could go like from like init or for uninitialized to initting. So it is like in an in-between state, and then you go to running. So it's just collecting jobs from a queue. But the user also had like the ability to like pause this thread or stop it. And and if you have like this sequential states, like it's still initting, it is done with initting, you really, I think you have to use the compare exchange mechanism, but I honestly not sure if like this is not so much used that this bugs really occurred. Maybe it occurred once and I just never thought about that. So that was quite a funny yeah, learning from all of this here.
Thanks. Interesting examples. Thank you.
I definitely find people where are, when I'm writing code, people are hesitant to use anything other than sequentially consistent, and kind of convince people that relaxed is fine when it is fine. Always takes a little bit of like, I promise it's fine. Really, there's nothing wrong that will happen. And it, yeah, I think if you're using atomics, it's probably because you want it to be fast. And you want it to be fast. You want to use the minimal restriction to allow the reordering that you need. But also, sequential consistency isn't that slow.
But that's related to what I was kind of getting at. It was like, we can't really just rely on LLVM to do all the heavy lifting for us, because like if I'm just using relaxed everywhere in my Rust code, that maybe works fine on x86, but not other places. If I only ever test on my own machine, maybe I'm not writing the program I think I'm writing, and I won't find that out until I try to run it somewhere else.
Definitely. And that's, I guess, where sequentially consistent becomes so attractive, because you're like, well, that's going to be the most the most secure on any platform. But I guess we kind of want to write our x86 code as if they could change it in the future, as if they didn't have that strong ordering already in place. We should write it how it actually should be, like the ordering that we actually need, not the order that we're accidentally getting. But that requires, yeah, definitely some head scratching. And if you get it wrong, like you say on x86, you're never going to find it. So you won't know you've made the mistake. Where are we at for time? All right, we only got 2 minutes, so I'll quickly just say, for those who, especially if you're new to this, the previous chapters are all on YouTube. I can drop this in the chat. We've also had talks on like Fearless Concurrency, Introduction to Atomics, Introduction to Async, and Rust Smart Pointers. If you're interested in this topic in particular, John Genset has a really excellent video as well. One of the Crust of Rust ones on just like writing a spin lock and all that, and it goes over a lot of the similar topics. I think it's a really nice like companion video to the book, because it's different, but it touches on a lot of the same stuff, talks about the different instructions kind of in like an offhand way for some bits of it, but when you're doing it coupled with the book, it really does start to all make sense, kind of.